think it's early on.
Is that force on the structure?
Yes, it's a pressure. P equals,
Yeah, 0.5 P air.
that's the one. Where's that?
It's clause 2.4.
Clause 2.4, thank you. Oh, there it is, excellent. All right, P, this is the other really important formula.
Well done.
P equals 0.5, that's actually rho air. V design theta squared, C shape, and C dynamic. Okay. And that is rho air equals 1.2 kilos per cubic meter. Okay. This is the formula from how you get from the wind speed to the pressure on a surface. So we have our sign, remember it looks like that. That's flat surface here. That's a flat surface. That's going to experience a pressure, a force on it. Okay? Pressure times area equals force. So it's going to experience a pressure. The pressure times the area of that sign will be this force trying to push that sign over. Okay? This V, site B, then becomes our V des theta. Our site speed becomes our design wind speed. Okay? So we're going to put 34.03 squared into there. C shape is what we'll do next. Before we go, let's go to rho air. Rho is a Greek letter, and that's the density of air. At sea level, the density of the air is 1.2 kilos per cubic meter. Everything I've ever designed uses that. If you, for some reason, design something at very high altitude, that number might change. If you're designing for other gases, I don't know, or something underwater. This also works for water, by the way. Just so you have a much higher density. Instead of being 1.2, it's 1,000. Okay? But it's the same formula. Air is a fluid, just like water. 0.5. Don't forget V squared. Okay? That's really, really important, and I say that from personal experience. Do not forget that squared. All right. Let's hit dynamic first. Chapter 6 is all about the dynamic factor. Basically what that is where you have a flexible structure and it sways back and forth in the breeze, it can actually start swaying in time with the wind, so the wind makes it sway worse and worse until it collapses. That's what the dynamic factor is all about. Okay? So it depends on, obviously, the geometry of your structure and how stiff it is, and its natural resonance period.
Isn't that why they make skyscrapers like the, what's the tallest one in Dubai? They have like offset layers?
Yes, that is all about controlling the dynamic factors. C dynamic is very complex. When I went through a seminar on how to do it, the overwhelming impression I got from it is, if you are a wind specialist and this is what you do, then yep, you deal with that. The rest of us don't do that. Okay, so it's fairly complicated. The nice thing is though that most structures, C dynamic is 1. You don't need to worry about it. Okay. Structures that have a natural period of more than 1 second. Okay. So if it sways and it takes more than 1 second to do a full oscillation, you have to worry about C dynamic. Until then, you don't really have to. All right. So it's really only very big and tall things. All right. So we're going to pretty much ignore C dynamic, and we go to C shape. Okay. In the older code, that used to be called C fig. So I might accidentally refer to it as C fig or C shape, but that's the exact same thing. All right, so we have that, we have that, we have that. Let's turn to C shape. And that is what the majority of your time in a code is going to be all about. Okay? So this is written with buildings in mind. So all the diagrams refer to buildings. If your building doesn't suit that shape, it takes engineering judgment to figure out what are the right factors to use. Okay? My advice to you is pick what you think the closest is, see how that looks. Then think, what if it was shaped kind of the other way? See if that factor is worse. And then, then you've got an upper and lower range. At least you can work in that range then. All right. with buildings, you've got internal pressures, you've got external pressures. If you have, say, let's cover one important thing first. If the wind is blowing that way onto the building, it's going to experience a pressure there on the windward wall. It's going to experience pressure here on the leeward wall. That's not supposed to be ends, that's supposed to be little arrows. It's going to experience an internal pressure, which might be inflation or it might be deflation. Let's draw it as deflation for now. And it's also going to experience a pressure on the roof. By the way, the internal pressure is the same on all those walls. Okay? The windward pressure and the leeward pressure are going to be different. And there's going to be a roof pressure, which is generally an uplift. Okay? So when you're analyzing that structure, you've got to go, what's the total sum of all those forces? What does it make the structure do? That's what the wind analysis is about. All right? But let's think about our sign here. And if I draw our sign looking that way, I end up with a sign which has a solid section here, the legs there. I don't know how that happened. There's our sign, there's the solid section, there's our wind blowing into it at 34. Everyone happy with that? All right. If you go to Appendix 2, I think it is. So it's got, the main chapter 5 is about the buildings, and then in some of the appendices they've got other structures from flags, flagpoles, antennae, like large TV antennas and stuff, silos and round structures, carports, free fabric roofs and things, and where is it? Hoardings and signs. Where are we? Appendix B. I think in the old one it's Appendix D. But freestanding walls, hoardings, canopies, and solar panels. Okay? And coming down here, we've got freestanding hoardings and walls. That's what that is, it's a freestanding hoarding. And so, in this diagram here, we've got a diagram of it, and it says that dimension is B, that dimension is C, and that dimension is H. Okay? And so we knew before that B equals 1.5, C equals 1, and H equals 2 in our example. Okay? That's the size of the sign we've chosen. Okay? So then if you look over the page, oh no, sorry, here is a formula. C shape equals CPN times KP. Okay, yeah, more formulas. And it says here, right, what it is. CPN is the net pressure coefficient normal to the surface obtained from table B2, and KP is the porosity factor. All right, so that says, is this sign solid or has it got holes in it? All right. Let's go first to CPN table B2. Table B2 is right over there, and the factor, shape factor, depends on the ratio of B to C and H. Okay, so you've got to figure out where we are on the table. So B over C, is it 0.5 to 5, or is it over 5? B over C is 1.5 over 1, so it's between 0.5 and 5. All happy with that? Okay. Go to the next thing, C over H. Is it 0.2 to 1, or is it less than 0.2? C over H, there's the C over H, is 1 over 2. So it is between 0.2 and 1. Okay, good. And so then we come to the formula. Oh, this is fun, right? Watch this. CPN equals 1.3 plus 0.5 outside of a bracket of 0.3 plus log in base 10 of B over C times 0.8 minus C over H. Okay. That formula is out of table, and I'll write that down, table B to A. Table B to A. Okay? That's that formula. You know, if we had a different C over H, it was a much easier formula than the next one down. All right. So, can we calculate that out? B over C is 1.5. So let's calculate from the inside. Can someone get the calculator? And we'll do this sort of verbally. What's log in base 10 of 1.5?
That's wrong.
Oh dear.
.176.